Welcome to qnawire.
In this case, we have a ideal reheat Rankine cycle, and we're going to look at varying the reheat pressure, or the pressure where we take the bleed off of the turbine. And so let's see here. Again, I'm just going to look at the efficiency, the specific net work. We have two quality factors to worry about. We can see one of them winds up, as we go from in this range here, we go from two-phase here to superheated, supercritical here. This is the exit of the turbine into the condenser, so that is always two-phase in this range here. It gets very close to being very close here to being saturated vapor. Pressure at the inlet to the turbine is again 15 megapascals in all cases. And again, I need to convert that to kilojoules. And then we have heat in, heat out, pump work in, which doesn't change in this case because, again, the inlets and the outlets aren't changing for this in this parameter study. And then the network, or the power out of the turbine. So we can see here, this is also kilojoules, is it not? This should be kilojoules. This has got to be kilojoules. Wait a minute. How did we get from here? Let me see here. Looks a little weird. Let me look at my code, see if I messed something up here. Oh, I know why. I didn't spit out the wait a minute. Oh, this is oh no, this is the work of oh, this is just the work out of the high pressure turbine. I didn't plot the work out of the low pressure turbine. That's why this is the high pressure side. I should have plotted, or should have got the work. This is correct. It's just we needed to add the specific work out of the low pressure turbine and then subtract this, and we'll get this. So technically, given all this information, we could get the work out of the low pressure turbine. So I was wondering why this and this weren't getting to this, because this is only the work out of the high pressure side of the turbine. Okay, so what can we notice here? Let's see here. Our efficiency goes up and then goes down. Our net work goes down consistently. Heat transfer in goes down. Heat transfer out goes down. So let's look at the plots for these things. Net work goes down as we go. Again, we're basically, as we get, the bleed pressure get up to the inlet pressure, then we're not really doing anything. So we really want to, be having the bleed pressure. Well, if we're trying to optimize the power output for a given flow rate, we want to basically have the bleed pressure as close to the exit as we can. But if we do that, we lower the efficiency. So again, we can see here that just because the power continues to go up, the efficiency actually hits a limit here. And so the efficiency is maximum, around 4 megapascals here. It doesn't change a lot. You can notice the scale; it's not a huge difference. But again, it's interesting to see that max efficiency, there's not the maximum in power output. Here is the two saturation points at 5. What did I put? I wrote the wrong. Did I write the wrong things over here? Yeah. This should be what are they? 5 and 7. So 5 is here, 7 is here, and so this should be 5 and 7. So you can see, 1 is, right here. So, we're two-phase in both cases for these lower pressures out here, which we might expect, right? Because this is going to be the same here. So as we drop this down, we're going to wind up going into the two-phase. Here I took 3,000 as the example here. So, we're slightly above 1. So we're slightly supercritical. And again, here's just the cycle here, here, through the turbine, a reheat, through the turbine again, and then back. So that's how this pressure here changes things.